Okay, so so we'll start with the charge sharing today. So um, charge sharing. So when I talk about charge sharing, so this is a charge shared between gate and source and drain, right? So so what we have studied, if you look at the MOS transistor operation, right, in the operation of MOS transistors, so we always assume that gate is controlling your body, right? So when you're so basically what it is, when you apply gate voltage, you have some charges in the silicon, and based on some charges in the silicon, your threshold voltage is defined, your current is defined, your capacitance is defined, everything is defined, right? So let's take example of this transistor. So here, um, at this is at a particular gate voltage. So definitely this gate voltage is more than flat band voltage, right? Um, so here, the gate voltage is more than flat band voltage. So I have a depletion layer in the device, right? And so if you see, um, so if I look at your threshold voltage, right? How do you means if you look at how we have uh, derived means how derived your threshold voltage. So if you um, so if you look at VG, so your gate voltage is nothing but your flat band voltage plus your oxide voltage, so drop across oxide plus drop across silicon, and when your gate voltage is between flat band voltage and threshold voltage, your Vox is nothing but your total depletion charge in the silicon divided by Cox plus Is, and also our threshold voltage also in defined in same way, right? So basically we'll have BFB plus 2 psi B. This is the maximum depletion width. So this is the maximum depletion charge divided by Cox, right? And we know this is BFB plus 2 psi B plus 1 by Cox, and maximum depletion charge is QNA 2 psi B. Okay, so this is how we defined our threshold voltage, right? So when you're talking about depletion charge, right? So so this is, so please, this the unit of depletion charge is per centimeter square, right? So the unit is per centimeter square. So we are talking about the charge below the gate. So basically, we are talking about this area, right? So total charge in this area, which is Q times Na times WD. This is the depletion width, right? Then this is the depletion width, right? And this is the total charge. And you're telling that okay, gate is controlling this charge, right? So when you change the gate voltage, this Q Na WD, this depletion charge will also modulate or will also change, right? And at some point your depletion width will be maximum, and after that you will have means inversion layer will start forming, right? Okay, so but if you look at very clearly, um, so another example, let's say our gate voltage is equal to flat band voltage, right? So when gate voltage is equal to flat band voltage, right, right? So that means there is no band bending, right? So there is no band bending in the silicon, there is no charge, but that is not actually true, right? There are some charge in the silicon because of your junction, right? So this is N plus, so your source and drain are N plus, and you have a body P-type substrate, right? So you have two junctions sitting, and there will be depletion charge across the junction, right? So and since this is N plus, right? So the depletion width in the source and drain is very small, right? So um, here your ND is around 10 to 20 per centimeter cube, right? So your source and drain are very heavily doped. Let's say your Na is around 10 to 17. Let's say your p-type substrate is doped with 10 to 17 per centimeter cube. So if you calculate the depletion width, so depletion width will be only on the p side, because n side is heavily doped, there will be no depletion width, and that is nothing but 2 epsilon si vbi by qna, right? Right. So this part we have, means we have seen in the PN junction when we are discussing about PN junction, right? So if you calculate with these numbers also, if you calculate, so you will see this depletion width will be in the range of 100 nanometers, right? So what I mean here, right? So even if you are applying flat band voltage to the gate, right? So there are some amount of charges in the silicon, right? And this charge is because of source and drain region. This charge is because of source and drain. These are not because of gate, right? I am not applying any voltage to the gate. So gate is at the flat band voltage, right? And this, if you calculate, so with typical doping conditions, so these are around 100 nanometers, right? Right. So this depletion width, right, is around 100 nanometers, right? So we are not giving any voltage to the gate, right? So we have some charges, but if your gate length is very high, right? So what we told in the last slide, right? Right? Okay, this portion of the charge, because this is below gate, is controlled. This is the charge. This below gate is controlled by the gate, right? But but if you see, so this portion which is below gate, some portion is coming from the source and drain, some charges is coming from the source and drain. But if the gate length is very high, right? Let's say your gate length is 1 micrometer, right? Your gate length is 1 micrometer, right? So that means, so your source and drain contributes very less amount to the total gate charge, right? Right. But if right, so here so same thing. So now, so this first case, your vg equal to flat band voltage. In the second case, your vg is greater than flat band voltage. That means uh, we have so gate also creates depletion region, right? So if I see, this is the portion which is instrumental. This is how, this is we are talking about, this is the total charge, right? Out of this charge, right, out of this portion, so this red portion is controlled by source and drain, right? This red portion is controlled by source and drain, because this is coming from the source and drain. This is the source and drain depletion part. And this yellow portion here, right, this yellow portion here is coming by the gate, right? So the total gate charge when you're using, means when your calculation, right? So when you were calculation, right, your gate voltage is VFB plus psi s plus QD by psi Cox, right? This Q depth is nothing but Q NaWd, but this contains both components, right? This Q depth is, let's say this red portion is Q1, so red portion is Q1 plus Q2. Q2 is the yellow portion, right? Right. But when the gate length is very large, right? When the gate length is very large, right? So this depletion width will be around hundreds of nanometer, let's say 100 nanometer, right? 50 to 100 nanometer, right? And if your gate length is much higher, let's say gate length is around 1 micrometer or so, so then this portion, this Q1 will be, right, your, so Q1 is contributed by source and drain, and Q2 is contributed by gate. But if your gate length is very high, your Q2 is more than Q1, right? Right. So this is so then we could think of that most of the depletion charge is contributed by gate, right? Right. But that will not be true when you reduce the gate length, right? When you reduce the gate length, so when you reduce the gate length, what will happen? So in this case, you see here. So let's say this is again Vg equal to VFB, but I have shortened the gate length. I have reduced the gate length, right? Right. So I have reduced the gate length. Let's say the gate length is your gate length is 300 nanometers, right? Right. Your gate length is 300 nanometers. So even if I am applying Vg equal to VFB, that means I'm not applying any gate voltage, right? Bands are flat, but I have some depletion charge already there. right? This is contributed because of the source and drain junctions, right? Right. And now, okay, so if I move to Vg equal to VAB, but your Lg, let's say Lg equal to 200 nanometers, right? Right. So you see, I'm not applying any gate voltage. Gate voltage is flat band voltage, but I have these charges which are contributed from drain. So this is already there, right? So you could think of uh, my gate voltage is flat band voltage, right? But if you look at the silicon, there are some charges available already, right? There are some charges available here, right? There are some charges means there are already some surface potential, right? Even at Vg equal to flat band voltage, there are some surface potential, right? There is some potential, and that means already even if at Vg equal to VAB, right? So when gate voltage equal to flat band voltage, we always tell okay, your drop in the your charge in the silicon is zero, your psi s is zero also, right? But that is not true here in this case. The last case, uh, if you, when your gate length is only 200 nanometers, you see, even if you apply Vg equal to flat band voltage, so there are some charges already in the on the silicon, right? And that will give you some surface potential, right? And that will forward bias, right? Already that means, and that means at flat band voltage also already some surface potential means there are some drop in the silicon, right? Right. So because of this, your threshold voltage will reduce because the surface is already means already have some surface potential at flat band voltage, right? You have to apply less gate voltage, right, to reach to 5e, right, to psi b, right. So your your threshold voltage will reduce, right? So this is charge sharing. This effect is called charge sharing, right? So if I put it in the equation way, so in equations, so I always write this Vg flat band voltage plus is plus your depletion charge by Cox, right? Right. So this is in the subthreshold region when your gate voltage is less than threshold voltage. Uh, so here I could write down. Um, so this Q depth, right? Okay. So just hold on. I have a phone call. I have to attend and come back. Okay, so uh, yeah, so here, so out of this Q depth, I could write down. Okay, let's say Q depth one is I could divide this to Q depth one and Q depth two, right? Two parts, right? And Q depth one is coming from the source and drain area, source and drain, and so here you see Q depth is divided between gate and source and drain, right? Right. So this. Then I could write this BAB plus IA. So Q dep 1 by Cox plus Q dep 2 by Cox. So Q dep 1 is, let's put like the contributed by gate, and Q dep 2 is contributed by source and drain, right? So in this way, so you see your this is already, so this part, right? Though this part is not given, is not controlled by gate, right? So this part is not controlled by gate, right? So since this Q depth 2 is already given by source and drain, so to achieve the Q depth, right, total Q depth needed for inversion, the depletion charge needed for inversion, I have to apply small small gate voltage, right? So your threshold voltage will reduce, right? So, or in another way, so I could write down your gate voltage. Actually, your gate voltage is, let me write down in this way, so not confuse you. So your gate voltage VFB plus IS plus Q depth contributed by gate, because this is gate by Cox, right? Right. So your, this we could write down divided by total Q depth minus depletion charge given controlled by source and drain divided by Cox. So here I could write down this as IS plus Q depth by means depletion charge by Cox minus Q depletion charge given by source drain by Cox, right? Right. So this is our traditional, this part. If you look, this first three is your traditional, we always start with, right? This is your means conventional get voltage, right? So then, and there is a minus part here, right? So this is this portion is, there is a minus part, right? So now I could write down your threshold voltage, actual threshold voltage is VFB plus IS plus Q depth max by Cox minus. So when I reaching Q depth max, some portion is already there because of source and drain divided by Cox, right? Right. So your threshold voltage is threshold voltage 0, that is without charge sharing, when you are not considering charge sharing for long channel transistor. So this is threshold voltage, and then I have a minus component, right? Minus, right? So this minus part, so this actually, because this part is contributed by source and drain. So your actually threshold voltage is your threshold voltage of a long channel transistor minus minus some amount. Let's say this is delta VTH, right? Right. So your VTH will be VTH 0 minus delta VTH, and delta VTH is a function of length, right? So your length increases, your delta VTH will increase, right? Right? Your length increases, your delta VTH will increase, and your VTH will reduce, right? So I mean, if you understand this, so because previously we are only talking about your charge in the silicon is coming because of gate, but that is not always true, because there are two junctions sitting, and this junction also gives you some charge, right? When your device is, your transistor is very long, right? So we could neglect those means junction charges coming because of the junction, right? But that cannot be neglected when the transistors are very short, right? Transistors are short, that means already there are some charges already available, so your threshold voltage will be lower, right? So if you now, if I plot your threshold voltage, right? If you see your threshold voltage of a transistor as a function of length of the transistor, right? So then so your threshold voltage was because length का सब तो change नहीं होना चाहिए, length का सब flat रहेगा, so it will be flat, or let me look it in red, right? So it will be flat. Then when the length is very short, it will start reducing, right? And this reduction is because of charge sharing, right? Because when your gate length is reducing, the charge contributed by source drain becomes a significant part of total charge, right? So your threshold voltage starts falling, right? So this is typically observed in all MOS transistors. Your threshold if you take a MOS transistor and plot threshold voltage as a function of L, threshold voltage as a function of length, you will see this difference, right? Okay. So means I hope you understand. I hope I hope that you are able to understand what I am telling. But still, if there are some questions, please.
So here actually delta VTH is constant, right?
Delta VTH is constant. That's true. But if you see, uh, I am worried about this Q depth contributed by source drain divided by Q depth, right? Right. Right. What is the, so okay? you have make a good point. Let's put it in this way. Right. If I take this equation here, I could also write down in this way. Max by Siox right. So this part is your typical, right? So I am worried about, see, basically when you reduce the gate length, this part increases, right? So
Yes.
if your q depth max, if the charge contributed by source drain becomes equal to the q depth max, right? So your threshold voltage will be zero, right? Because you could achieve threshold without applying any gate voltage, right? So this means this part is means this is the ratio of charge given by source and drain divided by total charge of the total depletion charge, right? So this ratio is responsible for threshold voltage reduction. And if your channel is long, right? If your channel is long, sorry, for long, if L long channel, right? If your channel is long, right? So your Q depth SD will be more than, sorry, is less than, much less than site, right? So that means so you could neglect this part, and you will have your threshold voltage, long channel threshold voltage.
Yes, sir.
So the drop across silicon will also depend on this charge.
Yes, exactly. I mean, as I'm telling you, right? So look at this plot here, right? Look at this plot here, right? So here I am applying get voltage equal to flat band voltage, right? But you see your silicon is fully depleted, right? Right? Because your channel length is so short that this could be depleted by this by the junctions, because junctions, when there is junction there is a depletion region, right? And when your gate length is very small, let's say your gate length is twice of your junction, um, right, your xp, right, your junction depth, right? That means even if you are applying gate voltage equal flat band voltage, so if you look at this part, right, this is fully depleted. That means there is a drop across silicon even if you are not applying gate voltage, right? And that drop across silicon, this is enough to forward bias this junction, right?
Yes, sir. So, like, which one will have more contribution from this charge? The drop across silicon or the oxide? Like, drop across oxide? Like, in deriving the equation, we only considered, like, we only separated the two parts for the oxide charge,
Hmm.
oxide voltage. So, like, is it that this drop across silicon is relatively very less affected?
Oh, yeah. See, when there is a drop across silicon, there will be drop across oxide also, right? See, the point is, see, don't think in that way, right? Right. So, see what I'm, okay. How do I explain it, right? So this when there is a drop across silicon, right, there will be a drop across oxide also, right? Because when I'm talking about there is a drop across silicon, that means there is an electric field, right? The moment there is an electric field, there will be also be drop across oxide, right? Right.
So, sir, it will be like in proportion to the thickness of the oxide and depletion there.
Yeah. So see, you only think of, see, you only think of in this way, right? Um, when you're applying some gate voltage, right? Uh, so before you apply some gate voltage, there are already some charges available, right? Right, and these charges will also contribute to invert your channel. That means you need to apply only less gate voltage, because source and drain is also contributing to the total charge in the silicon, right? So if your channel is long, the source drain contribution is very less compared to the gate contribution, right? But when the channel length is short, the source drain is also contributing. The source drain contribution is a significant part of that. That means they are since they are also taking part of in creation of charge, right? So gate contribution will be less. Gate contribution will be less means you need not apply very high gate voltage to invert the surface, right?
Yes, sir.
Right. So this is called charge sharing because see your transistor, MOS transistor is a gate control device. We always tell this is a gate control device, right? What do you mean by gate control device? Whatever charge coming to the silicon, that is only because of gate change in gate voltage, right? Right. But in this case, when you go into very short channel transistors, right? Very short channel transistors, so drain have a contribution, right? If you have see previously your channel length was very long, right? Right. So even if there is some source and depletion charges, their contribution to the total silicon charge is very less, right? But now your channel length is becoming shorter, right? So their contribution is becoming significant, even if they are not changing. So they are see the source and charge depends on the doping, right? N plus and P doping, right? Right. But that is fixed. But the point is when you that is fixed, but when you're reducing the channel length, but that part is becoming a significant portion of the total charge in the gate, right? So if you look at this here, right, if you look at this here, this case, let's say this case here, right? So you see your channel length has reduced. Okay, if I go to the earlier part, this is a long channel transistor here. So channel length is higher. So this yellow part, which is controlled by gate, and the red part, which is controlled by drain. So yellow part is much higher. So you could say that okay, red part is the contribution of red part to the total gate charge is less. But as you go on reducing the channel length, the contribution of source and drain will slowly increase, and it will. And when your gate length is very small, right? So even if you are not applying any gate voltage, your silicon is already depleted, right? That means you only have to apply very less gate voltage to deplete it. Means to more depletion, to have more depletion and to have inversion, right? So that's the reason. Since you are applying less gate voltage, so your threshold voltage is less. Since you're applying less gate voltage, your gate control will also be less, right? So that okay. So is it clear? So is it clear for all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this is the typical characteristic we see, right? The threshold voltage. So what you want, right? Your threshold voltage should be constant, right? You don't want your threshold voltage to change with L. But in modern transistor or in transistor, when you reduce the gate length, your threshold voltage will reduce, right? Right. So because of this reduction, so this is not desirable, right? So this slope part is not desirable, right? Why it is not desirable? I'll give you just one example. So let's say you have put your transistor in this way, right? You have designed your transistor. Let's say this length is 100 nanometer, right? So and you know, okay, this is the threshold voltage of the transistor, right? So this is the threshold voltage of the transistor, and let's say okay, so now and so you have designed a circuit with 100 nanometer long transistors, but during fabrication, let's say there is because of some variation your 100 nanometer becomes 90 nanometer, right right when it becomes 90 nanometer, your threshold voltage reduces. So you are planning for, let's say, this 400 millivolt threshold voltage, but what you actually get is 350 millivolt maybe, right? So your threshold voltage reduces, means all your things will be affected, right? Your current and all those things, right? But if you have a very good technology where if you have a very good technology where your charge sharing is properly controlled, and you have a very flat VTS versus L curve, right? Your VTS is not reducing with L, or when you reduce L. There, if there is some variation here, right? If any variation, right? So there is no change in VT, right? VTS. So your length, so length variation will always be there, right? So whatever you have drawn, right? So let's say you are designing, you are doing a layout, you are drawing something, right? But when you take it to the fabrication, there will be some change, right? If you have drawn 100 nanometer, you may get 110 nanometer, you may get 90 nanometer also, right? But if your VTHL curve is very flat, you will not see any change in VT with change in length, right? But in this case, right, in a typical case, so this bit means if you do not control this charge sharing part, right? So your transistor will be in the slope part. The transistor will be in the slope part, and there and any change in gate length will also change the threshold voltage. Any change in threshold voltage will change the off current, on current of a transistor, and you will do a lot of bad things, right? Right. That's the reason you means you design your transistor, means you have to minimize this called VT roll off, right? This is called VTS roll off, right? VTS roll off means VTS reduces when you go to certain gate length. You want to reduce, you want to minimize this VTS roll off, right? So there are different techniques to minimize VTS roll off. So if you see um, why, you see why this VTS roll off is coming, because you have a depletion width already existing, right? So the way to reduce this VTS roll off is to minimize this depletion, the junction depletion width, right? How will you minimize this junction depletion width? You will you can be done by increasing the substrate doping, right? Your Na, if you increase the Na doping, your your depletion width will reduce, right? The junction depletion width, right? So I'm talking about this part, right? Right. So um, so there is a depletion width, right? Let's say uh, I'm applying VG of flat band voltage. So there is some depletion width, right, which is undesirable. I mean, this is creating your charge sharing effect, right? So to optimize this BTS roll up, you have to reduce this depletion width, right? So that could be done by something called by changing the means basically by changing the this is P substrate by changing the Na, right? But you cannot really increase the Na of whole wafers, right? Whole doping. So you do some surface implants, right? So you put some surface implants. So basically, your at the surface you change the doping. You actually, if you look at a transistor, I mean transistor are at the surface of the transistor, right? Which is the active part of your transistor. So there you put lot of doping compared to the substrate, right? Compared to the body, right? So you put more doping here so that your depletion width in this region is less, right? So if you have more doping at the surface, your depletion width will be like this, right? Right here it will be less, then it will increase, right? And since you are only worried about the top part, your interface part, so your VTS roll-off can be reduced, right? So there are other techniques also. People use something called halo doping, right? Halo doping is uh, nothing but if you have, so you have your um, source and drain area, right? And this is your P substrate. So P substrate has some doping here, but you also have some halo. That means you somehow create the region here, which is little bit. If this is 10, I mean this is not P plus exactly, right? So you will create some region. So this is P region, but around the substrate, around the source and then you create a higher doping region, right? And this doping is called halo doping, right? Halo doping is, that means it is covering the source and drain area. So if this doping is 10 to 17, so this doping will be around 10 to 18, right? Right. So by doing this, you are also reducing the this depletion width, right? You are reducing the charge sharing effect, right. So these are different techniques to avoid VTS roll off, because VTS roll off this VTS roll off is coming because of charge sharing, and this is not actually good, right? So you want so this is not good. So we use different design techniques to avoid this. And as I told you, so there are a couple of things. One, you increase the surface doping, or you use the halo doping, right? So use the halo doping. Okay, so this is about chat sharing, and um, okay, any questions here?
सर
Yeah.
सर वीटीएच रोल ऑफ होता है उसको मतलब एज ए डिजाइनर मतलब कितना तक टारगेट करना चाहिए, मतलब कितने परसेंट तक उसका वेरिएशन अलाउड करना चाहिए फॉर बेटर सर्किट डिजाइन, मतलब कुछ ना कुछ
No,
तो
no, no.
होगा ही.
See, basically, you want to use the transistor which has a flat VTSL response, right?
Yes, sir.
So basically, you want to use a transistor which has a flat VTSL response, right?
Yes.
Right. If that cannot be avoided, so basically what you actually get is you get a roll off, right? So at very lower length, then see, because analog design you want to avoid this roll off, right? Analog design में क्या होता है? So variation has lot of impact on the mismatch and all those things, right? So you do not choose the lower gate length transistors. Right? Somewhere you operate somewhere here, right? Right, so that you see that okay, even if there is a variation around this length, so VTS is not varying, right? So you will not have this mismatch effect, right? Right. But for digital design, you actually use shorter transistors, right? Very short transistors, right? Because you want speed, right? You want lower delay. So you somewhere use here. So there things will be affected, right? So to avoid that, people means as I told you, right? So you use halo doping and other things. So when you use halo doping, you could correct it, right? You could correct it means you cannot really make it better, but you could correct it little bit. You could reduce the roll off a bit, right, by using halo doping, right? So little bit reduction in roll off also improves the transistor behavior, right? So means there is no rule ki how much where you have to use, but you means as a designer you could look at where you're operating, right? So if you're analog designer, you have VTSL roll off curve, right? You want to avoid the roll off portion, right? So you it means you operate somewhere, you choose a gate length somewhere where VTSL is almost flat, right?
Okay.
Sir, is it possible that due to halo doping, my VTS even increases than the previous flat line?
That is actually happens, right? So see why if you look at this blue one and the green one, why there is a higher VTS? This higher VTS is because I have added some extra doping around the N plus region, right? And when I go to very short gate length, right? See, okay, here I'll show you, right? Let's say I have a longer transistor. Um, I have a longer transistor and I have a halo, right? The halo doping, and I have P, and this is not actually P plus, but let's say P plus, right? Right. So, and for for a shorter transistor, if I reduce the gate length of this transistor here, so if I reduce the gate length of this transistor, right? So then I have N plus, then halo will become like this, right? So basically you see, so if you look at the surface here, right, in this case, right, it becomes P plus, right? So but in the long channel case, there is no change in the doping at the surface, but when you reduce the gate length, actually average doping in the surface increases. That's the reason this preferentially increases the VT only in the shorter gate length transistors, right, and it avoids the roll off, right? So if you have a so in so here if so let's say this is case 1, this is case 2, uh, okay, so you had a roll off, right? So because of halo doping, so in the long channel there is no change in threshold voltage, because if you look at this case 1 here, right, so there is no change in average doping at the surface. But as you go on shorter gate length, the average doping on the surface increases because your P plus also merges, right? They merge, right, and you'll see little bit increase here, right? So the roll off will reduce, right. So this is this part is case 1 here. So that means there is no change in average doping. There is no change in doping, but in this case 2, right? So when you have halo, when you do not have a halo, so the average doping at the surface is different, right? So you have a VT increase. Actually, VT increases. That's the reason it avoids the roll off, right? Am I clear?
Yes, sir. I was saying like I was doing a simulation in that for a 400 nanometer gate length, my VT was zero point 0.4. But for if I reduce the gate length to 100 nanometer, my VT became 0.48, and I had done halo doping.
Yeah, it will be right. So yeah, if you use halo doping, it will increase, right? I mean, did you understand why it should increase, right? You have not done halo doping, or you have done halo doping?
I have done halo doping. I was saying that even in comparison to the long transistor, my VT became higher.
Yeah, it is possible, right? So depends on what is the doping of this P region, P plus, right. So if this doping is higher, really high, so it will be like this, right. In modern transistors, right. When I'm talking about this 14 nanometer, 32, 28 nanometer, 22 nanometer technology nodes, your actually VT actually rolls on, right? And so it's like roll off, right? There is a VT's roll up, right? So this if you plot VTH as a function of L, this roll up is because of halo doping, right? They have excessive halo doping just to control the short channel effects. So actually VTH rolls up, right? But at higher VDS, we have not discussed DIBL, drain induced barrier lowering. At higher VDS, it will be if you look at higher VDS, the threshold voltage, so that will be much flatter, right? So this thing is there, right? So it depends upon what is the concentration of halo doping, right? If the halo doping is high, so your VTH will be more than the long channel transistors.
Yes.
So this is the job of a designer,
So, but
right?
it's
How you want to have your VTHL curve look like.
so, but it should follow a trend, right? Like
Hmm?
if we are reducing the length and we have done the halo doping, so VTH should increase. Like
Yeah.
it's so actually it was like very like it was somewhat jumbled pattern. So for 400 we were getting some VTH. For 0.1 it was increasing. Then again for 0.05 it was reducing. So
It will
like
reduce, right? Because it also doesn't help, right? P plus is not helping, right? If you're very short channel length, see,
okay.
yeah. So see, look at this green curve, right? So it will increase, but if the channel length becomes very small, it will again reduce because your drain is again, see, your depletion width is more. I mean, basically you are reducing the depletion width by making P to P plus, right? But if you further reduce the length, right, these depletion widths will also merge, right?
Okay, so these P plus are also like they are also not helping in that case for very short.
Yeah. That will not help. Then you have to go for more P plus, right? So so because means this. So if you go to very short channel length, you cannot avoid roll off, right? Roll off will be there,
Yes, sir.
but
Now
that could
understand.
be delayed, right? So where it is rolling off, that thing could be delayed. That could be delayed to lower gate length, right?
Yes, sir. Understood. So, sir, with length, we have to change these halo dopings also so that
No. You cannot change, right? Because your halo doping
acha,
is constant for all gate lengths, right? So
okay.
because if you look at the fabrication flow, right, you do halo doping which goes to all the transistors, right? All NMOS transistors, and you have a different halo doping for PMOS transistors, right? So
But
that means this halo doping. I mean, you think of this case one. In the first case, there is halo doping, but halo doping doesn't have any effect, right? But it comes into effect when the channel length becomes small, right?
yes, sir. Okay, so we cannot change halo doping. Like halo doping is something fixed
No, you could
for all
change the
lengths.
doping, you could change the concentration of the doping and all those things, right? during device design, when you're designing a device, you could change it, right? But once the technology is qualified, you cannot change it further, right?
Yes, sir.
Right. So when you are developing stage, let's say you are developing a technology, right? So you are doing all these experiments, right? You are doing all these experiments and fixing, and you have to fix your halodoping finally, right? Okay, this should be my halodoping, and this doping gives you a better VTHL curve, which is acceptable for to the designers, right? Right. Then you fix it there, right?
Yes, sir.
Okay. So one so here, so let's um, talk about the next thing, which is drain induced barrier lowering, right? So this is just the extension of the charge sharing, right? So charge sharing, we're not discussing charge sharing, we're not applying any drain to source voltage, right? Because you see, I started with that the n plus, and this is your gate, and both of them grounded, source and drain is grounded, right? But in actual operation, you are applying drain to source voltage, right? So what we have discussed earlier, that your threshold voltage, if I plot my threshold voltage as a function of VDS, right? Right, and drain to source voltage, right? Your threshold voltage is flat, right? So your threshold voltage does not change. Your threshold voltage is not it does not change with drain to source voltage, right? Right. But that is not true for the shorter transistor. In the shorter transistor, if you see, your threshold voltage changes with VDS, so it will be like this, right? Your threshold voltage continuously changes with drain to source voltage, right? As you increase drain to source voltage, your threshold voltage will change, right? So what I'm telling here, right? You could measure threshold voltage, your threshold voltage at different VDS, right? By applying different drain to source voltage, right? And you see that your threshold voltage is continuously increasing. Sorry, ulta ho gaya. Okay, the threshold voltage is continuously threshold voltage will decrease as you go on increasing your VDS, right? And that phenomena is called drain induced barrier lowering, right? So this barrier, so drain induced barrier lowering, right? And this barrier that we are talking about is the source to channel barrier, this barrier at this point, right? Because this barrier is responsible for electron injection, right? And if this barrier, and we know that, okay, this barrier is controlled by controlling the gate voltage. If you change the gate voltage, this barrier will change, so electrons are coming and we are getting inversion, right? So and that how this barrier is controlled by gate, this is the gate control, right? I think you got my point, right? So there is a, if I do um, this is the conduction band, right? So this is n plus p and n plus, right? And I am talking about this barrier, right? And this barrier is responsible for electron injection in MOS transistor, right? And I am controlling this gate, right? I am controlling this barrier by increasing the gate voltage, right? And how well this gate controls this barrier, this is your gate control, right? But in a very short channel transistor, your drain also controls that barrier, right? And which is a undesirable effect, right? Because we know from the beginning your MOS transistor is a gate control device, right? Right. So now drain starts controlling the device, then it becomes non-ideal, right? So so basically we do not want drain to control your source to channel barrier. That's the reason we have to design in such a way that this DIBL or drain induced barrier lowering is reduced, right? So this is undesirable effect, right? We have this effect, this is an undesirable effect, and we want to reduce this. So now designing your device, you want to reduce, you want to get rid of this undesirable effect, right? So let me talk about a little bit more detail. What is DIBL? What is drain induced barrier lowering, right? Um, let's take two transistors. One is long, um, right? And if I draw the band diagram, if I draw the band diagram, let's say if I draw the band diagram for this thing, right? So right, so this is the band diagram. So let's say this is my band diagram at um, VDS equal to 0, right? If I increase the drain to source voltage, your this will be pulled, so it will go like this, right? So this is at a different VDS. Let's say VDS equal to some volt, right? Some X volt, right? Okay, some volt, right? Some VDS, right? Right. But you see, when the channel is long, right? When the channel is long, so the VDS, even if you go on increasing this VDS, right? Right, your source to channel barrier is not affected, right? So this source to channel barrier is not affected. This is staying the same, right? But if you go to if you go to a short transistor, right? So let's say you go to a very small transistor, n plus, right? Go to a short transistor. So here, what you have seen, right? So we have just discussed in charge sharing. So let's say when I'm giving Vg equal to flat band voltage, right? So let's say both the depletion region is merging, right? So because of the junction, right? Because of the junction, so there is a depletion region, right? How will you plot it in the band diagram? In the band diagram, you could see it, right? You clearly see it in the band diagram, right? So see here, you have this part, right? Here in the band diagram, you have this part. What this part sees, this is charge neutral, right? That means this is charge neutral means at Vg equal to VFB, when I'm giving Vg equal to flat band voltage, right? So this there is no potential. This is charge neutral, right? This portion is charge neutral, right? This portion is charge neutral. There is no charge, right? But in this case, right, since Vg equal to VFB, there is some charges. So you will see your band will something like this, right? So there will be no flat region left, right? Right. So you could even see this will typically happen, right? Because if you go on reducing the gate length, your EC will behave like this because your so you could think of, right? So I am coming to this point, the length is becoming shorter, right? Right. Right. So now if I and now if I give some drain voltage here, right? Because the drain depletion will increase, right? Because when the source is 0, there is a natural depletion width, right? But now I have reverse bias drain, then the drain depletion width will be more than the source depletion width. So previously, let's say depletion width was like this. Now because of then it will be like this, right? So that means your drain depletion width is penetrating, coming towards source, right? So if you plot in the band diagram, you'll see this will come down, right? So this barrier will reduce, right? So here you see what I'm telling is you are not applying any gate voltage, right? You are not applying any gate voltage, but if you look at this, your your source to channel barrier is reducing. The moment source to channel barrier reduces, you will have injection, right? Because see, this barrier is just controlling, just holding the electrons in the source side, right? But now you're reducing the barrier, and actually we want to reduce the barrier by gate voltage, by increasing the gate voltage. Now even if gate voltage is same, by changing the drain voltage, your barrier is reduced. That means I am just injecting electrons by changing the drain voltage. That means drain is controlling that barrier, right? Right. And since drain is already controlling that barrier, right? So drain. So in this case, applying drain voltage has reduced barrier by some amount. Now I have to apply gate voltage to reduce a little bit more to have the threshold voltage, means have the proper inversion, right? Right. So this is called drain induced barrier lowering. This is undesirable because see the MOS transistor. We always tell MOS transistor is idle switch. Idle switch means this turns on or off only by the gate voltage, right? But now in this case, very short channel transistors, even if I'm not giving any voltage to gate, you could turn on your transistor just by your drain voltage, right? Because your drain is very close to source. and it could control that, right. So this is called drain induced barrier lowering. So because of drain induced barrier lowering, your threshold voltage, so if you measure your threshold voltage are different drain to source voltage. If your drain to source voltage is very low, you have some threshold voltage, but if your drain to source voltage will be increased, then your threshold voltage will reduce, right. This is because as you go on increasing VDS, this barrier will be reduced. That means already there are some electrons injected, your gate has to just give some more electrons, right. So your threshold voltage will reduce in VDS, and this is called drain induced barrier lowering. If you see in your transistor, if you measure threshold voltage at different drain to source voltage, you will see that your threshold voltage is reducing, right. So this uh, is measured DIBL. So if you want this slope is something called millivolt change in threshold voltage by volt change in drain to source voltage. So DIBL is given in millivolt per volt, right? So let's say per 1 volt change in threshold drain to source voltage, how much millivolt VTA changes, right? That is, and this number should be as low as possible, right? Ideally, it should be 0 millivolt per volt, but it is not. We will see in some transistor it is around 100 millivolt per volt also, right? Because this is for some such transistor. So this DIBL, so what I'm telling is, so if I do this IDVG, right, IDVG, and this is your VTS point, and so this is your IDVG in the log, right? So this is log, right? So let's say this is at a VDS of 50 millivolt. Then when you go to VDS equal to VDD, right, you will see that your transistor will behave like this, because your threshold voltage is reduced. So your this is the threshold voltage point, right? But your threshold voltage will reduce here, so you will have something like this, right? Right. So this curve is for a higher VDS, right? This curve is for the lower, same transistor. So, but your threshold volt, your off current, you see, your off current is affected because threshold voltage is reduced. And how do you measure your off current? As I told you, your off current is your ID when VGS equal to 0 and VDS equal to VDD, right? So since during the off current measurement, you are already applying a VDS of VDD, so your off current is strongly affected by this DIBL, drain induced barrier lowering, right? Which is not a desirable, means which is not desirable, right? Because of this DIBL, you have higher offset current and you will have high leakage and bad transistors, right? So we want to avoid that, right? How you want to avoid this? Only way to avoid is the same thing. You have to reduce the charge sharing, right? Because this DIBL is also a second order of charge sharing, right? Because we have already some charge sharing. Now, when you reverse bias the drain to channel junction more, you have more charge sharing. But how to avoid it? The main means the only way to avoid it by increasing the doping, right? If you increase the doping in this region, right? This region, channel region, you increase the doping, or you increase halo. So all those designs, all those changes you have to do, right? So you have to increase the surface doping, you have to introduce halo doping and all those things, right? So in this way, the DIBL could be reduced, right? So when I tell it reduce, the slope could be reduced, right? So maybe your VTH will be like this, right? So your threshold voltage is not falling very fast with VDS, it is falling slowly, right? So this can be done by increasing the doping or halo, right? Increasing the doping of the body or increasing halo, right? Or you have very good gate control, right? If your channel is surrounded by the gate from all sides, which is your FinFET or nano SIGFET, whatever you call it, right? So nano ARs or nano FETs, right? Nano SIGFETs, right? So basically, in those transistors, your gate is surrounding your channel. So that means your gate is very well controlled. This is your gate is controlled from one side, but there your gate is controlled from all sides. That means your drain control will be less anyway, right? So your, if you look at the means, basically we moved from bulk devices to FinFETs just to increase the gate control, just to reduce the DIBL, just to reduce the charge sharing effects, right? So so these are just the device innovations um, to enable scaling, right? Because when you reduce the gate length, you have these undesirable effects like DIBL or charge sharing is coming into picture. Just to avoid that, um, we went for this better gate control. If you have better gate control, then your DIBL could be less, right? Drain control will be less. Okay, so the unit of DIBL is millivolt per volt. So it just means if you want to characterize this, you just measure threshold voltage at different drain to source voltage. Then you find the change in threshold voltage by change in drain voltage, right? So that is your millivolt per volt, and you want it to be as less as possible. All right. So this is drain induced barrier lowering. Any questions here? So how many of you got this?
Sir,
Yeah, Nissan.
sir means after halo implant also means for the 50 nanometer gate length, I'm getting near about 40 to 45 millivolt per volt of DIBL.
Yeah, you cannot see. If you remove the halodoping, it will be even more, right? So your goal is to means reduce this, right? You cannot really avoid that this one, right? Because in short channel transistor, your DIBL will not be zero, right? There will be finite drain control, but you could only reduce that. You cannot make it zero. So the example that you're giving, if you remove the halodoping, your DIBL will shoot up. It will even be higher, right?
Sir, one more thing is for suppose we are designing in 180 nanometer technology, so means इस गेट लेंथ को बोलेंगे कि मीन्स इसके बाद शॉर्ट चैनल इफेक्ट स्टार्ट हो जाएगा या फिर मतलब
See,
एक्सपेरिमेंटली.
I mean, so short channel effect to 180 maybe start हो जाता है 180 nanometer itself, right? So see, the best way to look at right, is just plot threshold voltage for all transistors as a function of L, right? VTH as a function of L, right? So you could see a roll off, right? Right. So means if you want to do means if you want to avoid roll off, then choose a length where the VTH versus L is flatter, right? Right. So there is, I mean, I cannot really tell you what length the short channel effects will come into picture, right? But that, see, you could always delay the short channel effects by different device design methods, right? So to find out where the short channel effects are coming, which point the short channel effects are coming, so you just have to plot the device characteristic and see that, right?
Sir, here like VTH versus VD plot. So the characteristic of this plot, is it like linear or will it be
Not
some?
necessary. I just drawn it linear. It's not necessarily linear, so it will reduce with VDS, right?
Yes, sir. But it cannot be linear. No?
No. It is not necessarily, right?
Yes.
So maybe in some cases the VDS, when the VDS becomes very high, it reduces at a different slope, right? It might be like this also, right? It will reduce like this, right? So it is not linear, right?
Yes, sir. So, sir, DIBL and even SS, these things will depend on the point that I select, no? Like where I am measuring these slopes.
Of course. So basically, what is generally done is you give for DIBL measurement, you give VGS, which is very less, around 50 to 50 millivolt or 100 millivolt, right? And no, okay, sorry, not VGS, but VDS, right? You measure threshold voltage for VDS of 50 millivolt, very less VDS, and VDS of VDD, right? So this is the standard procedure, right? You measure VTH here, you measure VTH here. Let's say this is VTH1, this is VTH2. Your DIBL is VTH1 minus VTH2 divided by VDD minus 50 millivolt, right? This is the standard technique, right? You don't measure in between, right? Because see, you will use your transistor at anyway at VDS equal to VDD most of the time, right? So you
Yes.
take this point, and when the transistor is just means VDS is very less, that means it's a linear region, right? So linear VDS equal to 50.
So, sir, like these are for DIBL. So, is there any specific values for like subthreshold slope also, like few
Yes,
voltage
so I
values?
told you, right, how to measure subthreshold slope. I told you, right. So basically, see, the way to measure subthreshold slope is again, subthreshold slope will also change with VDS because of this
Yes, sir.
so short channel effects. So let's say you have this characteristic. So let's say this is for VDS of 50 millivolt, right? This is your ID in the log axis, and this is your VGS, right? So let's say this is your threshold voltage point, right? So you have to be deep in subthreshold region to measure subthreshold voltage, right? So if you know your threshold voltage and you know this point here, right? This, let's say this is at I threshold, right? Threshold voltage at sorry, the current at VGS equal to VTH, right? So you go actually 1 to 2 orders down this, right? So if this is ITH, then you go to ITH by 100, right? Take a point, then you find what is your VGS. Then you go to ITH by 1000, right? 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 Then that means there is a decade change in current, and there is a millivolt change in VGS, right? And this is millivolt per decade is this slope here, right? So this will be your subthreshold slope, right? This is how you measure, right? But you have to take a point very deep subthreshold, right? Not very close to threshold voltage point, right? And for that you have to make sure that your points where you're measuring your subthreshold slope is 1 or 2 decades below your threshold voltage point, right?
Yes, sir. These points basically I wanted to know because the slope is also continuously changing,
Yeah,
like
yeah,
from
yeah, yeah. So these are the standard procedures. So you cannot really measure here very close. Sorry, you cannot measure very close to this point. So
Hmm.
you know this current. I mean, you know the threshold voltage. You know what is the current you are getting, right? So you go 2 decades below. You go 3 decades below. Then you take the difference, right? The difference in this voltage, right? This will be your slope, right? A swing, right?
Yes, sir.
Because your current
Yes,
is already changing by 1 decade, whatever change in voltage you are getting here, that will be your successful swing, right? So,
subthreshold.
yeah.
Yes, sir. Yes, sir. Got
Sir,
it.
subthreshold swing is on a standard basis measured on VDS equal to 50 millivolt only, or we can measure it at any VDS.
Any?
Any VDS, any
No,
drain
no,
voltage.
VDS, again, if you look at VDS equal to VDD, right? If your transistor is long, you will not see any change in subthreshold swing. But if your transistor is short, you will also see a change in your subthreshold slope swing, right? Because your VTH has changed, drain has some control. When the drain, see you means I think you learned this thing, right? So this part is your gate control, right? How quickly your gate is going from off to on, right? That is your gate control, right? And that part
Yes,
is
sir.
your size VG plot. If I look at the size VG plot, right, your size is increasing and reducing. This part your subthreshold, right, where the size is increasing, right? Right. So this part is your gate control. This part is your actually your gate control, right? Since when the short channel effects come into picture, your gate control actually reduces, right? Since the gate control reduces, your slope will also change, your swing will also change, right? So you could, so basically, if you see typical transistor, if you go to any company or any fab or any PTK, if you look at, they specify subthreshold swing at 50 millivolt or 100 millivolt, very low VDS, and at VDS equal to VDD, right?
Yes, sir.
Yeah. So I mean, let me reiterate, right? This part is your gate control, right? So this part is nothing to do with the gate control, right? So gate control, when I'm talking about gate control of your transistor, so gate control is always the subthreshold part, right? How quickly your current is rising from off to on, right? How quickly your transistor is turning on, right? So think of this, right? When I'm talking about ideal switch, right? Ideal switch कैसे होता है? ideal switch is something like this, right? So your ideal switch will be, it will be something, it has a, means the slope is infinite, right? Right. So this is your ideal switch, right? So it is going from I off to I on, right? Right. This point is I on, right? But you're not talking about a transistor. Your transistor is something like this, right? Your transistor is something like this, right? So not, I cannot draw it properly, right? So this part is the problem of your transistor, right? This part here, right? Because your transistor, when you're turning off the transistor, it does not turn off quickly, right? It takes time to turn off, right? So it takes some continuously reducing, then it goes to off, right? Right. And when you're designing a transistor, the main goal is to make sure that your transistor turns on very fast, right? And that's the reason your subthreshold swing comes into picture, right? But unfortunately, your subthreshold swing is limited to 60 millivolt per decade. You cannot go below that. So this slope is, I mean, so you will have a slope, but you want to design your transistor so that your subthreshold swing is very close to 60 millivolt per decade. If it is more than that, that means it is in Morse, right? Right? So your transistor is not an ideal switch, but we want to design your transistor so that it is very close to an ideal switch, right? So that is the whole point of designing your transistor, how well you could design it. That's the reason people moved from bulb devices to SOI devices to FinFETs to nanosheet FETs, all those things people are talking about, tunnel FETs or whatever FETs. So this is just to make the transistor better, right? Better switch. It's clear?
Yes, sir.